This presentation provides an introduction to the use of probability distributions to model continuous and discrete random processes. Probability distributions quantify the uncertainty in random processes. They can be used to analyze data and make optimum decisions in uncertain or variable situations. If you ignore the maths, the main ideas behind probability distributions are quite simple. These ideas are demonstrated here using the Anderville distributions application. All the difficult maths and coding is contained within the MathNet numerics library, which is linked into the software. Practically all government, business and personal decisions involve some degree of uncertainty and risk. Some of the ideas behind quantifying uncertainty and making rational decisions are presented here. There are many types of random processes that contribute to uncertain conditions. Their output values can be continuous or discrete and may be limited in range. Although the output of a random process is uncertain, the relative likelihood of different values characterizes the process. Three examples of random processes are discussed below. Example 1 is a continuous uniform random process. A random number function is provided in most programming languages. These functions generate a single or double position number on a defined interval, usually between 0 and 1. All numbers on this interval are equally likely. A continuous uniform probability distribution is simulated below. Each time the sample button is pressed, a value is sampled from this distribution and assigned to the variable named randNum. After observing a number of samples, it becomes clear that the samples are restricted to the range between 0 and 1 with no preferred values. Example 2 is a binomial process. A binomial process generates a random number of successes in a fixed number of trials or experiments. This is a discrete process with a finite number of possible outcomes. The process is defined using two parameters, the probability of success and the number of experiments. Some numbers are more likely to be output than others. A discrete binomial distribution is simulated below. This distribution models the number of heads shown in 32 coin tosses. Each time the sample button is pressed, a value is sampled from this distribution and assigned to the variable named n heads. The observed samples are all close to the value of 16. Values less than 8 or more than 24 are rarely seen. Example 3 is a normal process. The normal process is the most common and can be used to model many natural phenomena. The process is defined using two parameters, the mean and the standard deviation. Numbers close to the mean are more likely to be output than others. A normal distribution is simulated below. This distribution models the heights in centimetres of adult males. Each time the sample button is pressed, a value is sampled from this distribution and assigned to the variable named height. The observed sample values are all close to the mean value of 178.4. Statistical tools are available to identify the type and parameters of a distribution that most likely generated a set of samples. Random variables are used in computer code and mathematical expressions to represent random processes. Uncertain conditions can be modelled mathematically by combining random variables in a formula. In examples above, the random variable named randNum represents a continuous uniform random process. N heads represents a discrete binomial random process modelling multiple coin tosses, and height represents a continuous normal random process modelling adult male heights. The outcome of a random variable or random process is not known until a sample is taken. A particular outcome of a random variable is called a random variate. Other outcomes or random variates of the same random variable generally have different values. Probability distributions characterize the output of a random process. A probability mass function, or PMF, is used to define a discrete random process. The PMF shows the probability on the y-axis corresponding to each possible outcome on the x-axis. The PMF shown below models the number of heads, or successes, resulting from 32 coin tosses. The sum of the probabilities of all possible outcomes is always 1. The most common outcome from 32 coin tosses is 16 heads. Outcomes of less than 8 heads or more than 24 heads are rare. A probability density function, or PDF, is used to define a continuous random process. In a continuous distribution, the likelihood or probability of a particular value being selected from an infinite number of possible values is theoretically 0. The probability density values, however, are non-zero, and the probability density function shows the relative likelihood of values. The area under the PDF between two values on the x-axis is the same as the probability of the random process generating a value in this interval. The total area under a PDF is always 1. The PDF of a continuous uniform random process is shown below. Outcomes between 0 and 1 are equally likely. The PDF used to model adult male heights is shown below. This is a normal distribution with a mean of 178.4 centimetres and a standard deviation of 7.59 centimetres. Different types of probability distributions have different parameters used to define the shape of the PDF. The shape of a normal distribution is controlled by setting the values of the mean and standard deviation parameters. Adjusting the mean parameter changes the position of the peak value of the distribution. In a normal distribution, the peak value is the same as the mean value. The standard deviation is a measure of how much the distribution varies about the mean value. Changing the standard deviation parameter changes the width of the distribution. And now we adjust both parameters at once. Points located at the mean plus 1 standard deviation and the mean minus 1 standard deviation are plotted on the PDF. The area under the curve between these 2 points is 0.6827. The probability of an adult male height within 1 standard deviation of the mean is 0.6827 or 68.27%. The central limit theorem explains why normal distributions are so common in natural phenomena. The sum of n greater than or equal to 20 random variables will be approximately a normal distribution, provided that the random variables are independent, that each has a finite variance, and that no small set of the variables contributes most of the variation. This general expression of the theorem is provided by Scott Page in his book The Model Thinker. The contributing random variables can have any distribution, and the sum will be approximately normal. The theorem is central because it plays a central role in probability theory, as noted by George Polya in a paper published in 1920. The probability mass function and the probability density function show the relative likelihood of sample values for discrete and continuous random processes, respectively. The cumulative distribution function, or CDF, is the integral of the probability mass or density functions. The CDF shows the probability that a sample will be less than or equal to a specified value. The probability that a sample value will lie within a specified range can be easily calculated using the CDF. While the CDF is a function of the sample value and returns a probability value, the inverse cumulative distribution function, or inverse CDF, is a function of a probability value and returns a sample value. The inverse CDF can be used to simulate samples from a probability distribution. The PDF chart shows the relative likelihood of output values from a random process. The chart below shows the distribution of adult male heights. The area under the PDF to the left of a particular random variable value on the x-axis is the same as the corresponding CDF value. This area is the probability that a sample will have a value less than or equal to that random variable value. The cumulative distribution function, or CDF, is generated by integrating the PDF. The CDF value at any x value is the probability that the value of a sample taken from the distribution will be less than or equal to x. This CDF value is the same as the area under the PDF to the left of x. The inverse CDF chart plots the height on the y-axis against the probability on the x-axis. This is the opposite of a CDF chart, where the probability on the y-axis is plotted against the height on the x-axis. We will see in the next section how this function can be used to simulate a specified random process. The area under the PDF between two random variable values on the x-axis is the probability that a sample value will lie within that range. The CDF makes it easy to calculate probabilities. For example, the probability that a height lies between 185 centimetres and 190 centimetres can be calculated by subtracting the CDF at 185 from the CDF at 190. This probability is 0.9368 take 0.8077 equals 0.1291 or 12.91%. Samples may be simulated from a probability distribution for many purposes, including model validation, hypothesis testing, Monte Carlo simulation, risk management, education and training. The Generate Samples form is used to simulate samples from a specified probability distribution. Sample values corresponding to larger probability densities are more likely than values corresponding to lower probability densities. A simple method of simulating a sample is by calculating the inverse CDF value corresponding to a random probability value. The probability of each sample value generated this way will exactly match the PDF of the specified distribution. The histogram tab shows a histogram generated from a set of simulated samples. A histogram is generated from a set of samples by counting the number of samples within different value ranges. As the number of simulated samples increases, the histogram should converge to the shape of the probability density function of the specified distribution. A histogram generated from 100 samples is shown below on the left, and one generated from 10,000 samples is shown on the right. The samples were simulated from a normal distribution with a mean of 178.4 and a standard deviation of 7.59, which models adult male heights in centimetres. As the number of simulated samples increases, the shape of the histogram approaches the shape of the PDF of the specified distribution. In the figure below, 200 samples were generated from 200 probability values uniformly spaced between 0 and 1. The samples are plotted with orange lines on the PDF, CDF and inverse CDF charts. On the PDF chart, the density of samples is proportional to the probability density. On the CDF chart, the density of samples is proportional to the slope of the cumulative distribution function. On the inverse CDF chart, the samples are shown as defined, uniformly spaced along the probability axis. These charts demonstrate how the inverse CDF translates the uniform probability density of a computer-generated random number into the probability density of a specified distribution. There are many ways of determining the parameters of a probability distribution to model a random process. The maximum likelihood estimation method, MLE, described here, can be used if a large number of observed samples is available. Probability distribution parameters for a set of samples are estimated by searching for the values having the maximum likelihood of generating the samples. This can be done in theory using the following steps. A set of probability densities corresponding to the set of samples is calculated for particular probability distribution parameters. The product of the probability densities provides a measure of the relative likelihood that the set of samples was generated by the specified distribution. The distribution parameters are adjusted until the relative likelihood value is maximized. In practice, probability density values are small, and the product of only a few values becomes too small to represent on a computer, even when using double precision variables. We can, however, easily calculate and represent the log of the product of the probability densities. This is done by calculating the log of each probability density value and summing the logs. Adding the logs of the values is equivalent to multiplying the values. The sum of the logs is the log of the product of the probability densities. The probability distribution parameters are estimated by maximizing the sum of the logs of the probability densities. These are the most likely parameters for the set of samples. This method is now demonstrated by simulating a set of samples from a specified distribution, then using these samples to estimate the parameters of the distribution used. The Multiple Samples tab of the Generate Samples form is used to generate 1000 samples. The Most Likely Parameters form is used to estimate the distribution parameters. Using the maximum likelihood criteria, the estimated distribution parameters are mean of 177.94 and variance of 7.54. This is close to the actual distribution parameters of mean 178.4 and variance 7.59. As the size of the sample set is increased, the estimated parameters approach the actual parameters. The figure below shows the calculations used to estimate the distribution parameters. For each set of estimated parameters, the log of the probability density is calculated for each value in the sample set. The sum of these values is proportional to the log of the likelihood that the parameters generated the set of samples. A simple search algorithm is used to converge on the most likely parameters. The maximum likelihood method can be used to estimate the parameters for any type of distribution. For a normal distribution, the mean and variance can be calculated directly from the set of samples. This section shows examples of using probability distributions for data analysis and decision making. A single probability distribution can often be used to represent random processes. In a more complex process, a Monte Carlo simulation is used to calculate a distribution from a number of component distributions. The PDF and CDF charts are shown for adult male and adult female heights. Adult male heights are approximately normally distributed with a mean of 178.4 centimetres or 5 foot 10 inch and a standard deviation of 7.59 centimetres or 3 inches. Adult female heights are approximately normally distributed with a mean of 164.7 centimetres or 5 foot 4.8 inches and a standard deviation of 7.07 centimetres or 2.8 inches. The data source for this data is Our World in Data. 68.3% of the adult female population have heights within one standard deviation of the mean, between 157.6 centimetres and 171.8 centimetres, or between 5 foot 2 inches and 5 foot 7.6 inches. 68.3% of the adult male population have heights within one standard deviation of the mean, between 170.8 centimetres and 186 centimetres, or 5 foot 7.2 inches and 6 foot 1.2 inches. The PDF curves show the relative likelihood of male and female heights. The CDF curves are used to calculate the probability of a height lying within any specified interval. Common Intelligence Quotient, or IQ, test scores have a normal distribution with a mean of 100 and a standard deviation of 15. Tests using this distribution include the WAIS 3, 4 and 5, the Stanford Binet 5 and Raven's APM. By definition, the mean IQ of the general population is 100. 68% of the population have an IQ within one standard deviation of the mean, between 85 and 115. The US Armed Forces have an admission IQ cutoff of about 83 on the standard scale. The PDF area corresponding to an IQ of 83 or less is shaded on the chart below. Applicants with an IQ in this range will not normally be admitted. This is nearly 13% of the population. People who attain an IQ score within the upper 2% of the general population qualify for Mensa membership. This corresponds to an IQ of about 132 or higher. This area is shaded on the chart below. The final investment decision, or FID, is a key stage in an oil or gas resource development project. Before investing in a project, a company will assess all possible outcomes to ensure an adequate investment return is likely with an acceptable level of risk. Because there is always some uncertainty in the oil or gas resource volume assessment, there is usually some chance that the project will not be profitable. The figure below shows the estimated resource volume for a discovered gas field. The gas volume units are billions of cubic feet, or BCF. The PDF and reverse CDF charts show the uncertainty in the estimated resource volume. In this example, a log normal distribution is used to model the volume uncertainty. In practice, the estimated resource volume probability distribution is generated by running a Monte Carlo simulation. The formula used to calculate the gas resource volume is resource volume equals gross rock volume times the net to gross times porosity times the gas saturation times the gas expansion factor times the recovery factor. None of the factors used to calculate the volume are known exactly, so probability distributions are used to define the uncertainty in the value of each factor. The Monte Carlo simulation model also includes estimates of any expected correlation between the values of different factors, as these will affect the volume distribution. When the Monte Carlo simulation is run, the values of each factor are sampled and the resource volume is calculated repeatedly until a stable histogram of the gas resource volume is produced. The calculation may need to be repeated many thousands of times to achieve this. The Monte Carlo simulation data can be used to produce volume distribution curves and key statistical values such as those shown in the figure below. Reverse CDF values are used in the oil and gas industry. The P90 value of 360.46 BCF means that the gas field has a 90% chance of containing more than 360.46 BCF of gas resource. The P50 value of 601.85 BCF means that the gas field has a 50% chance of containing more than 601.85 BCF of gas resource. The P10 value of 1004.88 BCF means that the gas field has a 10% chance of containing more than 1004.88 BCF of gas resource. Other key values annotated on the charts are the mean and the mode. Because the distribution is skewed, the mean and the mode values are different. Most oil and gas production companies will not approve the final investment decision unless the P90 resource volumes are profitable. In this example, if the P90 resource volume of 360.46 BCF is profitable, the final investment decision would usually be approved. Most of the examples shown above discuss data analysis and decision making based on a single parameter with a probability distribution describing the uncertainty in the value. If a decision is based on a parameter calculated from two or more random variables, Monte Carlo simulation is used to determine the probability distribution of the calculated parameter. A simple Monte Carlo distribution model is shown below. The model determines the uncertainty in the calculated area of a rectangle. Three cases are shown. The first with large length and width measurement errors and uncorrelated measurement errors. The second has large length and width measurement errors, but with correlated measurement errors. And the third example has small length and width measurement errors. These simulations were run using the Anderville Monte Carlo application. 1,000 trials were used in each simulation. In the first example, we calculate the rectangle area with uncorrelated length and width errors. In this simulation, the distances are measured with relatively high measurement errors. The errors have a normal distribution and a standard deviation of 15 centimetres or 0.15 metres. The length measurement has a mean of 5 metres with a standard deviation of 0.15 metres. The width measurement has a mean of 4 metres with a standard deviation of 0.15 metres. The length and width measurement errors are uncorrelated. The cross plot of the width and length measurements for each trial are shown in the chart below left. With no correlation, the points in the cross plot show a random scatter. The results of the Monte Carlo simulation are summarised in the chart shown below right. The calculated area has a mean of 19.994 square metres and a standard deviation of 0.966 square metres. In the second example, we calculate the rectangle area with correlated length and width errors. In this model, the length and width measurement errors are correlated with a factor of 80%. The cross plot of the width and length measurements for each trial are shown on the chart below left. Because of the correlation, the cross plot points tend to align along a linear trend. The results of the Monte Carlo simulation are summarised on the chart shown below right. The calculated area has a mean value of 20.012 square metres with a standard deviation of 1.283 square metres. In this case, the correlation between the length and width measurement errors has increased the error in the calculated area. In the third example, we calculate the rectangle area using accurate measurements. In this case, the distances are measured accurately with a laser ruler. The length measurement has a mean of 5 metres with a standard deviation of 1 millimetre and a normal error distribution. The width measurement has a mean of 4 metres with a standard deviation of 1 millimetre and a normal error distribution. The calculated area has a mean value of 20 square metres with a standard deviation of 0.006 square metres. In this case, with the accurate distance measurements, the error in the calculated area is negligible. So to summarise, when measurement errors are sufficiently small, deterministic calculations using exact input values can be used to generate an output value with negligible error. When measurement errors are significant, probabilistic calculations are used to quantify the uncertainty in calculated values. Exact input values are replaced by probability distributions. Any correlations between input values are specified, and a Monte Carlo simulation is run to reveal the probability distribution of the calculated output. An optimum decision can only be made when the full range and likelihoods of possible outcomes are known. Four of the most common discrete probability distributions are shown in the gallery below. A Bernoulli distribution describes the outcome, success or failure of a single trial. This distribution has a single parameter, which is the probability of success. The Bernoulli distribution is a special case of the binomial distribution where a single trial is conducted. The gallery shows three different examples of the Bernoulli distribution. The example shown in red models tossing a coin where a head is a success with a probability of 0.5. The yellow example models selecting a card from a deck with replacement where a heart is a success with a probability of 0.25. The blue example models rolling a die where a 6 is a success with a probability of 1/6 or 0.1666 recurring. A binomial distribution represents the number of successes in a sequence of independent Bernoulli trials. This distribution has two parameters, the number of trials and the probability of success in each trial. The shape of a binomial distribution becomes more symmetric as the number of trials increases. The shape approaches a normal distribution with a large number of trials. This distribution is used for modelling binary outcomes of repeated experiments in many fields. Three examples of the binomial distribution are shown here. In red, the distribution models the number of heads in 64 coin tosses. In yellow, the distribution models the number of heads in 32 coin tosses. And in blue, the distribution models the number of sixes in 64 rolls of a die. A Poisson distribution models the number of events that occur in a fixed interval of time or space where the events occur with a known constant mean rate. The parameter is the average rate of events. The Poisson distribution is particularly useful when the events are rare. Examples include the number of mail items received each day or the number of phone calls at a call centre per hour. Four examples are shown on this chart. One where the average rate is 1 call per hour in red. In yellow, where the average rate is 2 calls per hour. In blue, the average rate is 4 calls per hour. And in pink, where the average rate is 8 calls per hour. A geometric distribution models the number of trials required for the first success in a sequence of independent Bernoulli trials. The parameter is the probability of success in each trial. An alternate version of the geometric distribution is the number of failures before the first success. Three examples of the geometric distribution are shown on the chart. In red, the distribution corresponds to the number of die throws required for a 6. In yellow, the number of card draws required for a heart. and in blue the number of coin tosses required for a head. Ten of the most common continuous probability distributions are shown in the gallery below. A continuous uniform distribution represents an experiment where all outcomes are equally likely over a specified range. The parameters are the minimum value and the maximum value. Most programming languages include a random number function that generates a real number uniformly distributed between 0 and 1. A continuous uniform distribution could be used to model the position of an air molecule in a room or the position of a puncture in a tyre. The normal distribution is the most common distribution function for independent, randomly generated variables. The distribution is symmetrical with a bell shape and an equal mean and median located at the centre of the distribution. The parameters are the mean and the standard deviation. The sum of a number of random variables will be approximately a normal distribution. This is the central limit theorem. The normal distribution is also known as the Gaussian distribution or bell curve. This distribution is used to model adult male heights, IQ scores, and blood pressure. The exponential distribution models the time between events that occur continuously and independently at a constant average rate, which is a Poisson process. The parameter is the rate. The exponential distribution can be considered as a continuous version of the geometric distribution. This distribution could be used to model the time between arrivals of customers at a service point. The gamma distribution is a positive-only unimodal distribution that generalizes the exponential distribution. The parameters are shape and rate. The gamma distribution has a right-skewed shape. The distribution can be used for modeling waiting times between events that are Poisson distributed. The Cauchy distribution models the distribution of the x-intercept of a ray emitted from a point. The parameters are location and scale. The mean and variance of this distribution do not exist. It is used in robustness studies and used to model the ratio of two normal random variables. The log-normal distribution models the distribution of a random variable whose logarithm is normally distributed. The parameters are the mean of the variable's natural logarithm and the standard deviation of the variable's natural logarithm. The relationship between the parameter values and the shape of the distribution is not intuitive. The product of a number of random variables will be approximately a log-normal distribution. The distribution is used to model measurements in engineering, medicine, economics, and other fields. The beta distribution is defined over the interval 0 to 1 inclusive. A wide range of shapes can be specified using the two shape parameters. The parameters are shape parameter 1 and shape parameter 2. Distribution shapes can be symmetrical, left and right skewed, and U-shaped. It is commonly used in statistical modelling and Bayesian analysis. It can be used to analyse sports statistics such as baseball batting averages. The beta scale distribution is a version of the beta distribution with an additional two parameters that extend the range of the distribution beyond the 0 to 1 range of the beta distribution. The parameters are the shape parameter 1, shape parameter 2, the minimum, and the width. Distribution shapes can be symmetrical, left and right skewed, and U-shaped. This is a versatile, general-purpose probability distribution. The triangular distribution is a continuous probability distribution with a lower limit, an upper limit, and a mode within these limits. The parameters are the minimum, the maximum, and the most likely. This is a simplistic distribution used when limited sample data is available. The distribution is used in business and economic simulations, project management, and modelling natural phenomena. The Program Evaluation and Review Technique, or PERT, distribution is the same as the beta scale distribution but with alternative parameters. The parameters are the minimum, most likely, and maximum. There is also a scaling parameter, but in the PERT distribution this is fixed at a value of 4. The minimum, most likely, and maximum parameters allow easy specification of the distribution shape. The PERT distribution has the shape parameter fixed at a value of 4. The parameter can be adjusted, however, in the modified PERT distribution. This was originally developed for use in project management to specify task completion times. It is a popular distribution because it is easy to specify a symmetric or skewed shape using the 3 parameters. In summary, probability distributions provide a mathematical description of the likelihood of different outcomes in a set of random experiments. Many distributions can be combined in a Monte Carlo simulation to model and analyse complex systems and processes. Accurate models of the uncertainty in complex systems are essential for making good decisions. A range of uncertainty models are used in various fields including finance, engineering, biology, energy systems, and social sciences.